very excited to introduce our Colloquium speaker, Dr. Shengwang Du, today. And Dr. Du is a current professor of physics and Francis and Maureen Johnson Chair at the UT Dallas. Pioneer joining UTD in 2021. He was a professor of physics and the professor of chemical and biological engineering, and the director of super resolution imaging center at the Hong Kong University of Science and Technology, and elected a member of Hong Kong Young Academy of Science. Dr. Du's interdisciplinary and cross-field research activities range from fundamental quantum physics to applied optical engineering, including AMO physics, quantum optics, atom chip and electronics, quantum networks, quantum computing, quantum sensing, and optical neural networks for artificial intelligence, and optical microscopy for solid mechanics and bioimaging. And Dr. Du's PhD work on atom chips made an important contribution to the startup called Quanta. Now they call it Inflection, and now a leading company in cold atom technologies and neutral atom quantum computing. Dr. Du is co-founder of Light Innovation Technology USA for developing and commercializing advanced optical microscopies and bioimaging techniques. And Dr. Du is a professor of is a fellow of APS and OSA. So let's welcome.
Thank you, Professor May, for the introduction. So, first of all, for the people online, can you hear me? Please, okay. Okay, so yeah. So today I want to talk about the future of the distributed quantum computing with the S-QGPU. So this GPU is not a data GPU. Okay, so I will explain that later. Call it S-QGPU, but this GPU will be different from the GPU. So,
Right. That only one of the connectors. Sorry.
Water connect.
Yeah, it's not.
Oh. Okay, I will use my keyboard. So, okay, I think nowadays, quantum computing is very hot. So I will spend a few minutes to explain why the quantum computing potential is so powerful. And we know it now, the classical computer we are using, it deals with the bit and the 0, 1. So for the quantum computer, even we don't know how the future real quantum computer will look like, but we know the quantum computing we deal with called a qubit. Basically, in terms of the physics language, and this qubit means it's a superposition of 0 and 1. So classically, if I 0, 1, you either deal with 0 or 1. You cannot same time to do 0, 1 simultaneously. But in the quantum mechanically, we can make the 0, 1 as a superposition state. So that means the 0, 1 is present simultaneously. And this make it possible for the for the parallel quantum parallel computing. So let's make an example. For example, let's say if we have 100 qubit. So if you classically, this 100 qubit have if you look at the basis, the dimension of the Hilbert space of the qubit is about like 200 is about 10 to 30 power. So there's so many. So if you want to calculate this with for the classical computer, let's say you have function fx, and you want to calculate fx. Okay, all of those so many numbers you need to do a calculation. Okay, so if you do that one, even now, if you have a computer with 100 gigahertz CPU, okay, clock 100 gigahertz. Okay, so you want to do this 200, this one. So now here, so see, it take more than billion years, 100 billion years, to do the computing one by one. Okay, even this is very simple. So So that means it's impossible, right? Here you have 100, okay, but if you have 100 quantum qubits or the qubits, so that means you can make a superposition of all combination of these numbers. So you can import this to the quantum computer, okay, at the same time. Even this quantum computer is very slow. For example, you just do one calculation fx for 1 day. Does that just take 1 day to compute all of those numbers? So that is why, okay, a quantum computer is so powerful. Yeah, another image you can look at, the in terms of the helper space, the dimension of the helper space is this. So if you want to use it with classically, for example, let's use one single atom to store a bit. So you need it. So for the quantum computer, you just need, for example, 100, 300 qubits. But if you use classically to store this information, you will need more than the number of atoms in this unit. So in that sense, it's impossible. Okay, for the information transfer, but for the quantum, if you have and make a quantum computer with 300 qubits, okay, you already beat the entire universe. Basically, you don't need anything else. Okay, in this universe. So how a quantum computer looks like? So in the classical computer, we know is made of nodes and this logic, basic logic units. Then you build up the entire circuit. So for a quantum computer, let's say if you have n qubit, okay, fully connected. Okay, we say that n qubit fully connected universal quantum computer, it requires n qubit. So n qubit, okay, one qubit can be one atom or superconductor circuit, and also require single qubit gate operation. So that is basically 2x2 unitary transformation, and also you will need a 2 qubit control gate operation. So that means that in this n qubit, you can apply 2 qubit control gate operation between any 2 qubits. So that is called a fully connected. So if you have this kind of quantum computer, as I already mentioned, if you have 300 qubits, okay, it span out of the dimension of space, more than the number of the atoms in the universe for a classical quantum computer. So that's already powerful enough. Okay, powerful enough. So you can build the quantum circuit. Okay, so what is the reality? So in the reality, we have several known platforms. For example, the superconducting circuit. Okay, that's a work driven by the industry like IBM, Google, Intel, and the trapped ion. Okay, now a company called IonQ, Honeywell, and a neutral atom, Colloquium, for the inflection now. But if you look at the news release, since IBM, I think end of the last year, released called Condo with more than 1,000 qubits on the computer. Okay, so you say, okay, I say 300 qubits is very powerful, right? They have already 1,000 qubits, so that means they've already done all the job. But now if you look at you still don't see any practical applications from the IBM quantum computer. So the reason is that sometimes we get the qubits, the number of qubits is not really measured. As I showed before, you want that you have 40 connect. So I mean, any 2 qubits in the system you can talk to each other. But this one is not. So they even have more than 1,000. They don't have the the connectivity for all the qubits. So that means even in the future they build a million qubits, it's still not that useful. So that is the problem. Okay, for the superconductor qubit. For the trapped ion, I will say IonQ now probably only released 32. It looks like much smaller than this one, but this 32 is fully connected. But still far away from 300 qubits. And Colloquium, I think they plan to build more than 1,000 qubits in 2024. Okay, but nowadays we know still quantum computer is a dream, right? It's a dream drive our future, but we are not going to get that part. So that's the reason why we are here. We can have a job to work on this one to see if we can make a contribution. So look at the superconductor quantum computer, the qubit like 1,000, but in the physical realm, this is the layout of the qubits. Okay, for example, this is 1, 2, 3, 4, 5, and you'll see each qubit can only connect to nearby. So that means it's called a nearby coupling. Okay, you can only talk to the qubit nearby. So you can, so in the 1,000 qubits there, you cannot really from here to there. So you have to go through very many intermediate steps. Eventually get to talk to two qubit very fast. So it's not a fully connected. So that is the reason why they even have okay, more than 1,000 qubits. It's still not practically useful now, okay, to make revenue. And for the trapped ion, basically the remote gate operation make use of the cooling interaction. So cooling interaction have a distance, right? So you cannot go to very far away. So typically this is the distance between have to be limited by about 600 microns. I think exceeding 50 qubits, in the trapped ion is extremely difficult. Okay, extremely difficult. So the ion Q is only 32, but if you go to the 50, probably it's already exceeding this limit. For the neutral atom, make a random interaction. The distance is also about like 10 to 50 microns. So that means if the atom out of this region, you cannot directly have the interaction. So that will also limit the connectivity. So, okay. So that means to make a 300 qubit really fully connect the local quantum computer, it's really difficult. But it's much easier now to make a quantum computer with 10 qubits. Okay, so then I think that is really existing now in the industry, like IBM and Google. But 10 qubit you cannot really do much thing because you cannot build a classical computer. Okay, right? So since there's no reason for people to use. So now my idea is, can you connect two quantum computers together? Too small. It's just now we have a laptop. So it's hard for us to buy 1,000 qubits from the IBM, right? It's expensive. We cannot have that. But it's easy in the lab for them. We have 10 qubits. But can we connect with small quantum computer together right now with a laptop? Okay, your mobile phone. So if we connect them, so that means if you look at a Hilbert space in qubit, so each one have a Hilbert space of 2 of n. So if we connect them classically, just okay, I have 2 quantum computers, each one have 10 qubits. We just put it here. You connect with the wire. So then the Hilbert space is just 2n plus 1. So that means equivalently, you just have a single quantum computer, add 1 more qubit, but make this qubit have a connectivity with all the qubits. That's all. So that means it's not really that powerful. Okay. So, but if you can connect them with quantum mechanically, potentially the Hilbert space can be expanded to 2 in the power of 2n. So this is much more powerful. So for example, if you have 10 qubit, and if you connect quantum mechanically, you can make like 20 qubit quantum computer, and the power of the is much higher than individual quantum computer. So that is I think we hope, for example, if we have 10 qubit quantum computer, we connect like 16 computer together with how quantum mechanics is possible, then we can make a 300 qubit quantum computer. It's a super quantum computer, but it will be anything now in this universe. So that is my dream. Okay, I think in the future now, instead of now we have a computer connected to the Zoom, we have the online meeting. So in the future now, suppose now we have a local quantum processing units, and each one have a small number of the qubits, not a very expensive. Everyone can have that. Probably you spend a few $1,000s, and you can buy one, and then you can connect them together. Also, hopefully we have some cloud shared resource. Okay, nowadays we all connect to the cloud. For example, use ChatGPT. ChatGPT is not directly running your computer. Basically, you access the cloud service, and so then this will provide everything for this. So this is my dream about distributed quantum computing. So how to do that? But we still have to break down to physically say this is possible to connect them with quantum mechanics. So how to do that? So as a physicist, I would say, okay, fundamental probably quite simple. For example, if I have a computer A, computer B with three qubits, three qubits. If I connect them together, I move this one to there, right? For example, let's try to do some gate operation, entanglement or whatever. So after done, I move back here. Done. Okay, that's straightforward, right? So this is easy. But in the reality, this is not possible because if you have computer very far, even like here, you move your qubit from here to here, when you come back, probably you already lose the coherence of the qubit. We know the qubit is very not easy to survive. Okay, sometimes you cannot take it away from the vacuum, right? Most of the qubit will have to stay, probably in the vacuum, like for the atom. So you cannot really do this. Okay, so this is not a possible not to do this. Other possible way is, for example, this is the protocol. For example, if for each quantum computer, let's say you have a, I will call this called a computing qubit for the computing. And now this green one is for communication, okay, communication. And for example, if you can connect, let's say A and B, so if you can now convert this, for example, computing qubit here, convert to the photon, send the photon to here and convert it to this combination qubit. Then locally here, you can do the quantum computing. So this is another way that means you need to require converting to the photon, okay, converting to photon. So this is one possible way. Then, but now I think most popular way, even we don't have to do quantum computing, but if you look at the literature, there's a lot of proposal talk about, and mostly based on this, I would call this operation. For example, here we have for example, computing qubit here, and computing, this is green one is just for communication, not computing. So you find some way to untangle this communication qubit to build the entanglement. Right? Okay, if we have some way you build entanglement between these two green, and then you can do some local operation here. Based on some measurement, you can build an effective operation between here. So in this process, I will call the entanglement-communication-based distributed quantum computing. But here immediately you will see that the problem here is that for each quantum computer, for example, you have 3 qubits for the computing, but you need to have 3 additional qubits. Okay, but a qubit is very expensive. It's just like your laptop. You need to make every laptop very powerful. Okay, you have more double number of the qubits, so it's very expensive. Okay, it will cost a lot of resources. Okay, and so that's that another problem is using the entanglement protocol. The entanglement protocol is based on the measurement, and this is not a deterministic. It is a probability operation. So that is the existing the distributed quantum computing protocol using for the entanglement distributed quantum network. First of all, you have an entanglement quantum network for the green one, and then locally, for example, if you want to talk, this qubit here and this qubit here to make for some remote, gate operation. So the way is you build an entanglement between the green using some way. Okay, once the entanglement is built, and then you do the local operation here for green and blue, and then do some measurement. So this measurement mostly like real state measurement. Based on the measurement results, and you tell this one, you do another operation here. Then effectively, you do the entanglement on this one and this one. So that is how it works. So this basically is neither, first of all, based on the entanglement between green one. Okay, so you need to have additional qubit here to increase the cost. The second, it does not do direct operation from here to here. You need to local operation here, local operation here, based on the measurement. So the measurement within the quantum mechanically, it's always probability, right? It's always probability in your result, either this one or that one. So that means this process is non-deterministic. Okay, it's based on the measurement. Yeah.
The calibration protocol involves measurement, but it's deterministic. Because, you do something depending on the result of measurement.
okay.
So I don't.
So I think as the teleportation scheme is very similar to this. Teleportation scheme basically do this. You have entanglement from green and green. Then this one, you do the local measurement based, right? Then based on the measurement, you send this measurement to here, okay, to here. And in principle, if you can measure everything, it can. But in the reality, for example, the Bell space measurement, most of the time you can only access half of the space. For example, if you use a photon inspirator, you can only have access the half of the, so it's still probability. Theoretically, if you can access all the measurement result, you can increase this efficiency, but in the reality, yeah, it's always not probability. So this is similar to the teleportation scheme. Okay, teleportation scheme is based on measurement. Okay, based on measurement. So my dream is about this because assume I don't need the accumulation qubit. Why I need that? It's too expensive to have a qubit. Okay, so I only have necessary hardware in each quantum computer. For example, can I move this quantum qubit to the middle here? For example, in this architecture, I call it distributed quantum computer with shared quantum gate processing units. For example, in the middle, okay, in the cloud, I have a set of the 2 qubit gate operation here. Each box here, once again, so this is 2 qubit gate. So it's just a collection of them, okay? And if I find a way, for example, if I want to do the remote gate operation between this qubit and this qubit. So let's say if we can convert this qubit into the photonic qubit and send to here. So look at which qubit gate, which gate here it is free, okay? And so for example, here you convert into the this atomic qubit, this atomic qubit, then those are 2 qubit gate operation here. So after this process is done, you convert this qubit back to the photon, send it back here, and send it back, convert it back to the atoms. So in this way, you can do the remote gate operation, but without need of this combination qubit in each local quantum computer. But you have a combination qubit here. So this is like a bank, maybe some server, right, over there. So can be shared by all the local computers in this system. Also another way, this one does not depend on any measurement. It just needs converting qubit between, for example, this qubit to the photon, convert it back. So it is deterministic. And another way you will say, okay, looks like the total number of qubits is the same as previous, but you will remember here in this cloud, each 2 qubit is separate. There's no need of interaction between this gate and this gate. So that means in here, the cost is linear, depending on the number of the gates you have. It's linear. So as a practice, I know if you have a local quantum computer, you want to have a 4 connection. The cost is exponentially increased because you add 1 qubit. This qubit needs to interact with all other qubits. But in this system, you convert that law. Cost to linear. So this is here, it's linear. Even say it's very expensive to make this module, but as number increase, it just linear. Eventually will be cheaper than a local quantum. So this is how we compare these 2 pictures. So I did some estimation. Okay. So in terms of reasonable money, I find out, okay, so this is if you want to build a local quantum computer like the idea you put in. Okay, you want to build a 300 qubits. Okay, for example. So in this case, let's look at, we have 6 nodes. Okay, 6 nodes. So each node have n qubits. Okay, so that means you connect them together. Okay, so if you have 50 qubits each one, so multiply 6, you get 300 qubits. So if you want to build a single quantum computer, okay, like IBM, okay, the cost in terms of that one, so this is probably impossible. Okay, I think if you use all the GPT in the Earth, you are not able to build it. But if you use the entanglement-communication-based protocol, you still break up not too small. I think the cost is lower than this. Okay, but if you use the way I proposed for the S-QGPU, and because in that module, you reduce the cost in the local quantum computer. Okay, you don't need a connectivity, so you put a sand to the middle, that's shared by everyone, so the cost, I think when the number increase, it'll become significantly cheaper than, than this, okay, than this. And here's another picture shows you, okay, this is the number of nodes, and this is the number of qubits in each local quantum computer, and this is the, the cost curve, okay, and you will see when the number of nodes is very small, then it approach, okay, basically like a single quantum computer, you will think, but when the number of nodes increase, and the cost of the S-QGPU will be significantly cheaper than, this entanglement communication-based, the scheme, okay, this is. So, okay, but that is the dream, but how to do that? We need to find the physical mechanism to achieve that. I think now the bottleneck is if you want to come for the computing qubit into the photon, you need a conversion. And if you look at the real world and the existing quantum computer for based on superconducting circuit, single ion trap, single atom, and single quantum dot or whatever you have, all based on single atom picture. Whether this single atom is real atom or artificial atom, it's a single atom. So you have a discrete energy label, you have a qubit, and you'll find out all based on this efficiency is less than 10%. Okay, maybe not approaching 10%, but it's very low. So the reason is very simple, because for a two-level system, the quantum cross-section in free space is proportional to lambda squared, so wavelength squared. Okay, so that means the cross-section is very small. So that means the light single atom interactions, the cross-section is very small. So that's the reason I think this conversion efficiency is very small. And you can argue, say, okay, can we put the atom into the cavity? Okay. So that is okay. If you have a single qubit, you can improve the coupling efficiency between the photon and the qubit. Okay, but the problem is if you have many qubits, have a quantum computer, have many qubits, how could you many qubits into a cavity? So that is a challenge sense. You can control one, that's easy, but you want to control many of them individually. So you can, okay, I just put a cavity on each one. So, but those atoms separated by a few microns. Okay, you put a cavity for each one micron. Theoretically might be possible, but in reality, this is really challenge. Okay, so this is, I will not say physically not possible, but just in the reality, this is not a good solution. So my solution is use a ensemble instead of a single atom qubit. Okay, imagine now I have an atomic ensemble. So here I have like a million atoms, million even to billion atoms, and they act as a single qubit. So one sense now you can increase the interaction between photon and many atoms. Okay, so then this is my possible way, to do that. So how to do that? Okay, so this is the picture. So first of all, this will try to use a photon atom hybrid approach for the quantum computing. So we know for the photon, it is very easy. Let's say with the polarization of the photon as a qubit, okay? And it's very easy to manipulate a single photon qubit operation with just linear optics, with like a half-wave plate, beam split, quarter-wave plate. You can do the single qubit operation very much easier. Undergraduate students here, you can do that. Okay, you don't cost any money. Only thing difficult for the photon is if you want a photon talk to each other, control each other, that's difficult. Okay, a single photon control another photon. Normally this requires very, very high nonlinearity. So normally when we talk about nonlinear optical, you talk about a very strong, high intensity light. So single photon is very, very weak. So it's not that easy, okay? And so the idea is that if you want to do a two qubit gate operation, we convert photon into the atom. So this atom I show is many atoms. Okay, and then in the atom to atom, you can have some gate operation. Okay, those are two pairs. So that means that you make the single photon for the single qubit operation. Then if you need two qubit operation, convert into the atom. If you can make this one happen, we can realize my proposal of the experimental quantum computer. So this is one of the scheme. I talk out how to do that. So let's assume, okay, we have the two photon coming in. One is called a control qubit photon, another target qubit photon. And then let's assume now we encode H polarization with 0, V with 1. Assume this is the block box. Okay, inside there's some atoms inside. And this box will do one thing. Okay. If you import 0, 0, it output 0, 0. If you import 0, 1, output have a phase. Okay. Negative 0, 1 have pi phase. 1, 0, 1, 1 also have a phase. So if you look at the matrix in the base, you'll see this is the matrix. But we call it a control phase gate because depending on the state of the control, right? So you get a phase, phase difference, and we call it control phase. If you can realize this one, you pretty much close to the universal quantum computing. So I will explain that to you today. So how to make this happen? Okay, and to understand this one, we need a little bit some basics. So first of all, I need to convert the photon into the atomic ensemble very efficiently. So here we call this called electromagnet-induced transparent atomic quantum memory. Basically, that's is a quantum memory. So how that happens? So suppose we have a photon coming in, and this is our atom with, for example, 1 million atoms. Okay, they all prepare in the ground state, and we have another ground state here, but a little bit energy different. But this is some intermediate excited state. So we have a laser light. Okay, just couple these two states, and we put all the atoms here. And when the photon coming in, the photon, the wavelength is tuned to the resonance from this transition. So when the photon coming in, one atom, because this is one photon, okay, then one of the atom will absorb it, and then you turn off this light, this is called control light, so the atom will be transmitted to here. Okay, and because you have one single atom here, but you don't know which atom it is. Okay, basically the state of atomic ensemble is in this entangled state. So this means the first atom in this state, other atom is in this ground state, and this is the second atom here. So depending on which one, we don't know which one. Different position. This is the phase from the photon. Okay, you are generally in this state. So next, if you want to read out this photon, what do? You apply this control light, get back this photon, and you release the photon. But when you release this photon can come from all these possibilities here, and you have phase turn here. And they will maximally interfere in the same direction. So then this photon remember the direction of the photon coming in and also reference. So that's what we call this called quantum memory. If there's a storage photon in the system, then you read out after time. And because in this system, this is two ground state, it can be lived for very long time. Okay, and then you can store there and read out. I will call this called quantum memory. And the efficiency, and we demonstrate a few years ago, and we can achieve that for a single photon qubit with the efficiency you store in and read out. The total efficiency is more than 85%, and the fidelity can be more than 99%. Okay, so this is we solve the interface problem. So we can convert the photon into atomic state and then read it out. Okay, that's because we are not using a single atom. We are using many atoms. Another element we needed to understand is the system working. Okay, we need to know the radial oscillation. I think for students here, if you take, so you probably, how many of you are taking quantum mechanics? Okay, so you are taking, right? So you know the radial oscillation, right? If you have two systems, you have the interaction between, okay, you have the radial oscillation. And if you solve this, okay, so you solve this one, this is basically the evolution operator, and you get this, and you, okay, if you initial state, let's say, okay, and here you will see, this is basically this called rapid oscillation, right? Frequency given by the laser power. So in the reality, this is you have laser, you turn the frequency to the energy difference between the two levels, and this is the rapid oscillation frequency proportional to the electric field amplitude of the laser field. Okay, basically is the power. So if you make this, for example, the rapid frequency over time equal to pi over 2, normally we call it pi over 2 pulse. Okay, if there's a pi, there's a pi pulse, 2 pi pulse. So we solve this one quantum mechanics, we'll find out if initially in the ground state, if you apply pi over 2, you can generate a superposition state, 50% in ground, 50% in the excited state, but without phase difference. So I use this diagram to describe. But if you have a high pulse, you can turn from ground state 100% to excited state. But you have some phase here. Okay, so I use this one to represent. But if you apply 2 pi pulse, and this will, you will go back, okay, to the original state but have a negative sign. Okay, 2 pi will have a negative sign. Okay, if you want to completely the same sign, you have to run 4 pi. 4 pi you will get a positive. So I use this one to represent that. So this is called a radial oscillation. Another effect that in order to make the atoms talk to each other, we'll need this called Rutherford block effect. So how that works? For example, if you have 2 atoms, okay, they're sitting in the ground state, but we know the atom is you have electron move around the nucleus, right? So if this electron, for example, we know we have principal number n. So when n increase, the electron will be far away from the nucleus. Okay, so let's say this we call it when the electron is very far away from the nucleus, and we call it called Rutherford state. Okay, so when the electron get into very far away, for example, the electron is away from the nucleus, the electron is here. Then when the electron distant from is from that from classroom, so then this electron will be occupied in high class. So they can talk to everyone. Okay, so when this far away, for example, if we excite this electron, so this Rutherford state and electron atom become like very big. So it will talk to this atom, have interaction with the electron in this atom. So it will shift the energy level up. Okay. So in this way, if you want to apply another light to excite this one, you find that this energy level is missing. So you just stop this process. And this is called a Rutherford block effect. So one atom block, another atom is excited. Okay. So that means if I excite to here, is it now you can be excited with that Rutherford state. So that's the Rutherford block effect. So with those in mind, I will show you how to make this hybrid, the 2 qubit gate. So let's assume, okay, we have this is the many atoms atomic sample, okay, and this line represents the photon is coming in. So let's say we have a photon state, 0, 1 coming in. So 0, 1 means here. So 0 means here. So that means this photon will go through here, and this photon will go through here. So that means here you only have 1 photon. Okay. So that is called 0, 1. So if you have 0, 1 means you have okay, when this photon is coming in, basically you only have a photon here. So this is a control qubit, there's no photon come to that quantum memory I described before. So then you do the memory operation, and you will absorb that photon that convert into excited 1 atom here. Okay, but in this one, because there's no photon coming in, so you just have this. So you apply now. The way we do is apply a pi pulse in the control qubit here, but apply pi pulse from here to here. But because there's no atom here, So then this pi power will do nothing, okay, do nothing. And the second, do a 2 pi pulse, okay, in the target qubit. So after 2 pi radial oscillation, what do you get? You get a negative sign, right? You get a negative sign, as I showed you before. Okay, after that done, you apply another third pi pulse to the control qubit, but because there's no atom there, so they do nothing. So effectively, when everything come back, okay, you 0, 1 becomes a -0. So that's what we realize is one step. So let's not assume we input is 1, 0. Okay, so 1, 0 will do this. So we have 1 photon coming in. We excite the atoms here. So now you apply pi pulse. Okay, you will get a rainbow state. Then you apply 2 pi, but there's no atom here, so this 2 pi will do nothing. Okay, then you apply pi pulse to bring back this atom. So if equivalently this is 2 pi, right? So you'll get a negative sign here. Okay, so there's a 1, 0 on negative 1, 0. Now let's assume we have a 1, 1 coming in. Okay, if you have 1, 1 coming in, so basically you have 2 photons at each, 1 photon each. You get a side, but now you get a 2 pi. So they strip the angular label of that one. So it will block that excitation. So that excitation power will do nothing. So then you apply the pi pulse, another pi pulse. So equivalently, you have negative sign here. You don't have negative sign on the other side. So this also give you a negative sign for the state. So then basically this goes you realize this is called a control phase gate. Okay, control phase gate. Okay, so this is how to do that. But here you will require 2 atomic memory. Okay, but also you need to put these 2 very close to each other. That might be not that easy because so another way we can propose is imagine now we just have 1 quantum memory. The photon have a polarization, right? Polarization, so we can convert the V, these 2 into different mode. For example, both be coming here with the PBS. You can convert 1 photon with H, 1 photon with the V. So in this way, the 2 photon will overlap. Okay, in the same quantum memory will make maximum efficiency of the quantum memory. And there's another scheme, I will not go to the details, can also help to realize, the same operation. Okay, that's the same operation. So once we have that, so we call this called a CP. So mostly if you look at a textbook or the wiki, say, you need this kind of called C-NOT gate. That's the analog to the NOT gate in the classical computer. So C-NOT gate is just this. Okay, if you have 0, you output 0, 0, 0, 1, 0, 1. But if input is 1, the first bit is 1, it flips the second bit. So that is called a C-NOT gate. Okay, it's a standard. So here I will show you, if you realize a CP gate here, you just need to add some quarter wave plate, okay, before this target qubit photon. Okay, this is a 90-degree means the slow axis, orientation of the slow axis. Okay, and you can do the simple math, and you can turn this CP gate into a C-NOT gate. So this is a symbol of the C-NOT gate. And here we calculate the, okay, because there are 2 things important. One is fidelity of the gate. Okay, so fidelity of gate, another is efficiency of the gate. So because here the quantum memory of the efficiency. Okay, from here we show this C-NOT gate performance as function of the quantum memory efficiency. What quantum memory efficiency is needed? It's very surprising you see for the fidelity, even we have 50% efficiency, so fidelity can be still go up to like 95%. But the efficiency is linear because if the memory you have like 50% and you have 50% chance, the photon get lost. Okay, you don't get a work. So we have but the fidelity is high. So the reason here is because in this scheme we combine the photon. So if the photon get lost, it just get lost, you don't get it. Okay, you will not, when the clock get lost, you say, okay, I don't want that one. Okay, when you get the photon, it is right. So this something different from the, this single atom superconductor qubit quantum computing, because that one is, you have this, for example, qubit there, superconductor. Even something is wrong, that qubit is there. Okay, sometimes you don't know whether it's wrong. That's why you make a mistake. But here, if photon get lost, it's lost. You know it's wrong. Okay, this will help improve the fidelity. Okay, it's different from other systems. So then if you have that units, this units, I'll use this to represent the units. You put it here, so then this picture will work. Okay, if you know how to convert it, for example, right, photon, single, this is a qubit into the photon, then go to here, due to the gate operation, I already explained to you. Okay, this is how the picture works. Okay, so the difference as this thing as previously. So for the existing quantum computer platform based on superconductor, chapter ion, neutral atom, and other thing, I think the number of the computing steps is determined by the declining time. The declining means a pure quantum state after a while become mixed state. Okay, mixed state. So, but as a atom or the qubit is still there. Okay, it's still there. So the decoherence reduce the pure state into mixed state, so which reduce the error, increase the error, and decrease the fidelity. But for this hybrid photon atom, distributed quantum computing platform, the number of computing steps is determined by the photon loss. It's no more than by this coherence of this atomic system. So the idea is because once the two qubit gate operation done, you release the photon. And this atomic system go back to the ground state. Okay, it doesn't matter the coherence time. It's all you recycle. Okay, you don't need to keep that atomic system in coherence. Only since when the photon coming in, you just need to prepare. After the gate operation is done, it's done. It is released. Okay, so that is not determined by the atomic coherence, but it is determined by the photon loss, because once the photon get lost, the efficiency will get lost. So that how many steps you can do, it defines the photon loss. So another difference for the photonic loss, as I already showed you, remove the photon from the computational basis. Basically, you don't get it. So when you don't get it, say that's something wrong. So it will help you to keep a high fidelity when it is right. So there's something different from the existing other platforms. So then eventually, okay, so this is I think my dream. Hopefully, we can build this architecture. Okay, so I think yeah, time is how many minutes left? Yeah, okay, so almost now I will just briefly introduce my other direction. So this is okay, in my group, I have 3 different areas. So all connected by opticals. So first area for the quantum computing and quantum network. The second area we are developing all optical neural network for AI computing. And the third area, I think we are doing the quantum sensing and bioimaging by developing the optical microscope. So this is the work we developed. I think is the first deep all optical neural network. Okay, and for the quantum computing, and we of course the system is small. We have 200 input neuron, 20 hidden neuron, and 10 output, and we can use that one to successfully recognize handwriting. 0, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, and this is I think the first time the multi-layer optical neural network has that. So another direction I develop called optical microscope for the live cell imaging, and so this is our in the lab developed system. So eventually we'll commercialize becomes a product, it's quite neat. Okay, this is different from product in the, in the lab, we care about make a work public paper, right? So, but when you go to product, you have to have a lot of engineering involved. I think last year we get 8 million, Series A finance invested, and we found a company in the US and commercialize, the product. So the company is run by my students. So this is my existing, the team in the UT Dallas. So I will also acknowledge support from Air Force, and DOE and NSF. So thank you. Yes.
A naive question. Is it very challenging to provide photonic communication, say for a real world application, to a remote, your photonic connections? Is that very challenging to keep, the photonic coherence, I guess you need?
Okay. That's not okay for photonics. The coherence is not changing. It's because photon is not really coupled to the environment, right? Because as well as you build with other frequency, you mix with sphere light, you can very well. So the coherence of photon is very well preserved.
They can use conventional technology.
Yes, that can use fiber, use the particle fiber network to propagate the photon. So that's quite, I think, well developed.
I know that the polarization coding of qubit is problematic because there can be like just material defects that rotate polarization. That's very difficult to keep coherence.
Yeah, I think you're right. So that's I think if you want to use this one, you have to solve the problem when very long distance of preserve, the polarization. That's a technical.
Have you considered other encoding paradigms like frequency encoding?
Yeah, I think that's possible. But here I use a polarization, but I think it depends. Also, it's not people can use a photon number, so you can, certainly theoretically, okay, I think no one prevented you to do that. But for some specific system, I have to narrow down to which scheme I will work on. Yeah. So that will motivate different people to work on different things, right? Yeah.
You discussed a fully interconnected 300 qubit quantum computer. If you had one, what would you do with it?
It will make me very rich. You buy a big house. Okay, that's I think that will require I think many people for engineering. They will want to develop iPhone, people will develop many app. So I think I don't have to do everything, right?
Yeah.
So that's beyond my, I will focus on make this one. So then I'll give it to everyone here. So you will come up with new ideas, right? Program, make develop app. You will solve a lot of things. I think probably that is I will probably relax for a while after that.
I just have maybe a very good question about so how many atoms do you already have in the signal?
So here, okay, for the data efficiency, like 85%, I think that I need like close to billion atoms. Yeah. It's 10 to it's about like 100 million to billion.
When you say 85%, over how long can you hold that?
Oh, so in this, okay, in my demonstration, so that can be about like 2 microseconds. But some people, good at to increase that time. So it's not a single person not good at everything. So so some people can make I think like the professor makes postdocs group, right? They can make them probably close to milliseconds, right? Which is a kind of lattice of that. Right?
I have a question. So, you mentioned that you have this shared, point of, what's it?
S-QGPU.
Right, so, you have to like convert that, like the computing qubit to a photon, to this like shared, unit, and then you want to like send back this photon, use this for like convert the state, like. So I was wondering like you are like more focused on this, like the processing unit. I was wondering how, do you think it's like an impossible way to like to generate or like conversion the green could be the photons?
Okay, so that means you want to develop the local quantum computer with interface. So one way is to use a quantum ensemble to develop the local quantum computer. So it is a challenge to connect, those IBM, those quantum computers. So they need to solve the problem how to convert it into photon. But no matter what, if they want to connect to outside, they have to convert it into photon. So they have to solve this problem. Another way is use atomic ensemble picture to build the the local quantum computer. Right.
Is this a shared unit like works for other platforms?
Yeah, as long as you can convert it to the photon, then this is shared. It doesn't matter where this photon comes from, right? Yeah. But you have to convert it to the photon as a, for the communication.
This might be a silly question, but within your central node that every other computer is communicating with, could you also do photon conversions within your communication bits to potentially increase efficiency?
Yeah. So for example, if you want to do very long distance, you need to go to electron wavelengths, right? So this is a picture does not prevent in the middle. You may have a lot of different things to connect. Yeah. Right. Yeah. I think this is one student's feedback.
Another question.
Yeah.
What is the difference really between having that centralized like group of qubits versus having just like an old school switchboard where you plug things, but it's photons, and you use nonlinear optics? Like, why not just use a switchboard?
Okay. If you have nonlinear opticals, you can do it. Then you don't convert to photon, then you can do it. Okay. The thing is, as I already showed you, photon, single photon to single photon, it's a direct, that's difficult. Right? If you can direct it to the single to photon gate, then you don't need it. That one, you don't need this. But that's very challenging.
Okay, but I mean, the switchboard could be operated strong static fields.
Yeah, so I say, if you find that I can do this, then you will be more advanced than this. So this one, because I don't, that's why I combine to the added, then use the added to do that. If you can directly, do that with photon to photon, then that will be more advanced than this. Yeah, so you possibly can make that happen, right? So I hope that this will motivate you, for your future. Okay, right, yeah.
Very much.
I say it's not 10, but in 10 years, you might solve this problem. Yeah. Yeah.
Okay, we don't have questions. So if there's no more questions, or if there are further questions, you can put up to later. And let's say, thank you.